Welcome back to multivariate calculus. In this video, we're going to be looking at the tangent and normal vectors. We'll get to normal in just a moment. Tangent, I think, makes a lot more sense based on what you remember from previous study of calculus of a single variable. The biggest tool, the biggest reason that we cared about the derivative of a function in calculus of a single variable was that it gave the slope of the line tangent to the graph of the function at that point. And so now that we're talking about three-dimensional curves, we are still looking for lines tangent to the curve at a point. So let me get my head out of the way and let me draw in a curve. And I'm assuming that this curve is in three-dimensional space, but if you look at a small enough region of the curve, you can find a two-dimensional plane in which the curve resides. I don't think it's too much of a stretch to just assume that's something we can always do. But remember that if we have our coordinate axes somewhere, there is an origin. If this curve is the graph of a vector-valued function, r of t, let's use a different color. But if this curve is the graph of a vector-valued function, that means that at every point t, there is a vector r pointing from the origin to the curve at that point. And if we let time progress a little bit, there will be a vector pointing to the curve at that next moment in time. And continuing onward, we could go backwards in time. We can go forwards further in time. We get all these vectors pointing from the origin to the graph at various points. And our goal is to find for a particular point, let's say this one, we're looking for the line which is tangent to the graph. And geometrically, we can describe that the same way we described the tangent line previously. We want the line through r of t1 and r of t2 when t2 is infinitesimally near t1. So find a point that we care about, and then the next instant in time, where does the vector valued function point? And we want to go through that point as well. All right. So to find the distance between 2 points, or to find the vector pointing from one point to another, the vector between v1 and v2 is simply v2 minus v1. And so here, if we want t2 to be infinitesimally, well, getting ahead of myself. If we want the vector that goes through the point r of t2 and r of t1, we simply subtract them. And if we want t2 to be infinitesimally close to t1, then that means that we're really looking at r of t plus some small bit that I'll call delta t. And that gives me a vector pointing in the direction that I care about. Now, every multiple of this vector also points in the direction that I care about. And for reasons that I think everyone is catching, following along, the convenient multiple of this that I want to think about is the 1 over delta t multiple of r of t plus delta t minus r of t. Because, wait a second, if I take the limit of that as delta t tends towards 0, getting the infinitesimally close points that we cared about, I've just gotten back to the derivative. That's incredibly convenient. The derivative is going to get us the tangent line for a vector valued function and a parametric curve the same way it gave us the slope of the tangent line for a function of one variable. All right. So as an example, let's find the equation of the line which is tangent to the curve given by the vector valued function 2 cosine t I hat plus 2 sine of t j hat plus t k hat at the point root 2 pi over 4. The first thing that I need to do in order to solve this is figure out the t value, right? If I know the value of t for which the vector points to the point I care about, that is an important step along the path. In this particular case, if I look at the z component of the function t and the z coordinate of the point we care about, pi over 4, I have to be choosing the value of t that gives me that t is equal to pi over 4, which is easy to figure out. We can double check if I put t equals pi over 4 into the x component, 2 times the cosine of pi over 4 is the square root of 2. And I can check in the y component, 2 times the sine of pi over 4 is also square root of 2. So this point absolutely does work. We're looking at a point that is on the curve and we know when it happens, and that's important. The second thing we need to figure out is the derivative, r prime of t. Right? Differentiating a vector valued function is not too terribly challenging. You look at each component on its own and you differentiate that component. The derivative of 2 times the cosine of t is negative 2 times the sine of t. The derivative of 2 times the sine of t is positive 2 times the cosine of t, and the derivative of t is 1. So now we have r prime. Once we have r prime, we need to look at that function at a particular value, the value we've already selected, t equals pi over 4. So we get negative 2 times the sine of pi over 4 I hat plus 2 times the cosine of pi over 4 j hat plus k hat, which is going to be negative root 2 I hat plus root 2 j hat plus k hat. All right. That's all of the information that we need to ascertain from the original curve. At this point, we have everything we need. We know the point we care about, and we know the vector along the tangent line. So to summarize, the problem has now simplified to write an equation for the line through square root of 2, square root of 2, pi over 4. Parallel to the vector negative root 2i plus root 2j plus k. That's a problem that we know how to solve. The vector is always going to be in the form, right? I've already used r, so I guess I'll call this one u. U of t is going to be the vector pointing to the point in question, which is root 2, pi over 4, plus t times the vector parallel, negative root 2, 1. And expanding that out, writing it in unit vector notation if we want to, root 2 minus t root 2 I root 2 plus t root 2 j pi over 4 plus t. Okay. All right. That is our vector valued function whose graph is going to be the line tangent to the curve at the point of interest. And if I switch over to GeoGebra, we can graph this curve. We can graph the tangent line, and you can see that it does in fact intersect tangent to the curve at that point in three-dimensional space. All right, so there is one task very similar to a task that we've learned about before, but not the only task that we might want to look at here. Right. I'm going to come back to this model to look at it in a practical sense more closely, but let's jump back over to our notes sheet for a bit. And again, imagine that this is a curve in three-dimensional space, not just two-dimensional space. And at every point on the curve, we can draw a tangent vector. And as the curve moves, the tangent vector is going to change in size, or change in size and change in direction. Of course, every multiple of the tangent vector is also a tangent vector. So relying on the one that we found immediately isn't the best idea. And for that reason, we often look towards a unit tangent vector. Just take the tangent vector that we found, divide by its magnitude, and that gives us a unit tangent vector, which is convenient only because all of these tangent vectors are now the same length. And so when the tangent vector changes, right, the change in the unit tangent vector over time is never going to be a change in length. It's always going to be a change in direction. Now, here's the, I guess I could call it a stretch. I claim that the derivative of the unit tangent vector is always perpendicular to the tangent vector itself. I want to stress here, the derivative of the unit tangent vector is always perpendicular to the tangent vector. The derivative of any tangent vector is not going to have that property. That's something that only happens because we are setting the magnitude to constantly be 1. So the only way that the tangent vector can change is as a change in direction. And that property of changing direction means that we have to turn in some way, right? No matter which way the tangent vector is going, a change from that tangent vector to the next one is never going to be a change in length, right? Distance is going to stay the same. The thing that is going to change is the angle. And if you look at the triangle, that angle is not a right angle by any stretch. But there again, if we're looking infinitesimally close, we're looking at a vector that's going like that, and the next vector that is going like that. So the angle here is 0, which means that the two angles here are pi over 2 each in order to get that the total of the three angles of the triangle are equal to pi, 180 degrees. I think this is the weirdest thing you've likely seen as far as infinitesimals go, as far as calculus goes. When you are looking at unit vectors changing, that means that the direction is changing. And if you get them close enough, well, the change of angle in an infinitesimally small time step is infinitesimally small, and we can treat it as 0. Since the vectors themselves are both unit vectors, they have the same length, and in an isosceles triangle, the two angles that are touching one of, but not both of the sides of the same length must have the same measure. So we take the total measure of 180 degrees, divided up among the three angles. One of the angles gets 0, the other two evenly split 180 degrees to be 90 degrees each, perpendicular lines. All right. And so On our next example, we can find a unit vector, or a vector normal to the curve we were just looking at the point we were just looking at. I specify here a normal vector, not the normal vector, because just like the tangent vector, there are infinitely many. It likely will be convenient for us to find a unit normal vector, or it often will be convenient for us to find the unit normal vector, but finding a normal vector is good enough. All right. We've already established that this is going to be the point where t is equal to pi over 4, and we've already established that the derivative of this thing is -2 sine of t I hat plus 2 cosine t j hat plus k hat. All right. The order of our steps here matters. We need to take the derivative of the unit tangent vector and evaluate at a point. All right. So we need to take the derivative of the unit tangent vector and evaluate that at the point. That means we can't evaluate the vector at the point yet because we haven't taken the derivative yet. That means that we need to make this a unit vector before we take the derivative of this thing. So there is our order. We need to first find the magnitude of the tangent vector as a function of t. And in this case, it's always the square root, square each component. -2 sine t squared is 4 sine squared t. 2 cosine t, the whole thing squared, is 4 cosine squared t. And then we have 1 squared, which is 1. Notice here, and the reason that vector valued functions that we analyze so often have sines and cosines in them is very specifically for this step when we can say, oh, we have a sine squared and a cosine squared. And the Pythagorean identity says that sine squared plus cosine squared is 1. Which means that the magnitude of this particular function is the square root of 5. It's a nice constant value. We don't have variables going on. Taking derivatives from here is not going to make us want to curl in a ball and cry, and that's really important. All right, so now that we have that, we want to take our vector valued function, we want to divide by its own magnitude, which is going to have components -2 over the square root of 5 times the sine of t plus 2 over the square root of 5 times the cosine of t plus 1 over the square root of 5. And I forgot to include my unit vectors because I'm talking faster than I'm writing. Right? I hat, j hat, k hat still have to come along for the ride. All right. And now that we have our unit tangent vector, the normal vector is the vector perpendicular and can be found by taking the derivative of this thing. And taking derivatives of vector valued functions when the function isn't that bad is fairly straightforward. We can take the derivative component by component. Derivative of -2 over root 5 times the sine of t is -2 over the square root of 5 times the cosine of t. Derivative of 2 over root 5 times the cosine is the negative of 2 over root 5 times the sine. And then in the z direction, the derivative of the constant 1 over root 5, I'm sorry, derivative of a constant is 0, z term goes away. All right, so this is our normal vector. For certain applications, we may want to take this a step further and find the unit normal vector, but for right now, I'm going to leave it alone as this. At this point, we have our function for the normal vector, but again, the thing we're looking for is the normal vector at a particular point. So we can go ahead and plot in our values. In this case, it was t is pi over 4. And get that normal vector evaluated at pi over 4. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. The 2's cancel each other out. So we are left with negative of 2/5 in the j direction. I was planning to also plot this normal vector in GeoGebra so you could see how it works. But unfortunately, GeoGebra is fighting with me right now, so I'm just going to jump from here to one for you to try. Let's clear some space here. So let's find the tangent and normal vectors for the vector valued function two times the cosine 3t, 1 negative 2 times the sine of 3t at the point one square root of 3. All right, so see what you can do with that one. Spend a few minutes on it, and I'll see you in the next video.